Welcome to my presentation on the paper GIST, Efficient Data Encoding for Deep Neural Network Training, written by Animesh Jain, Amar Fanashai, Jason Mars, Lingjia Tang, and Gennady Pechimenka. Forgive me if I've butchered the pronunciation of any of these names. I'm Ian Kelk, and let's get started. Before we dive into the details of the GIST paper, we need to establish some background motivation of what problem it solves. What is image classification? What are CNNs? What are feature maps? So let's start from the very basics. We're going to start with something that's trivial for humans, which is image classification. Here we have an animal. What is it? Most people are going to say it's a dog, but can we say it's something else as well? What if we're looking at a whole lot of dogs and we want to identify a particular dog? See, it's also a Pomeranian, a specific type of dog. Now let's try a really hard test. Any guesses as to what this might be? You almost certainly got this one right, so congratulations, because computers have been part of our daily life for 40 years, and it was only about 10 years ago that they started getting good at this kind of thing. Humans are fantastic at this, even being able to identify things they've never seen before. If you teach a 5-year-old what a car is, and then tell her that a taxi is a yellow car with a hat, she'll likely be able to pick one out of a photo. I don't know if you've been to Mexico City, but I'm guessing that given the statement above, pretty much anyone could figure out which of these cars are Mexico City taxis. Until 2012, computers were kind of terrible at this. There's a competition called the ImageNet Large-Scale Visual Recognition Challenge. It's an annual computer vision competition that uses subsets from the massive ImageNet dataset, which contains 1.3 million images separated into 1,000 classes with different granularity of labels, like we showed with the dog Pomeranian example. Up until 2011, models did rather poorly and never did better than 25% accuracy. Then something happened. That something was the advent of convolutional neural networks. Alex Krizhevsky used a CNN called AlexNet to win that year's ImageNet competition, dropping the classification error record from 26% to 15%, an astounding improvement at the time. CNNs are a type of artificial neural network that are well suited for image classification because they reduce the number of connections needed by using a series of convolutional layers. Each convolutional layer applies a set of learned filters to an input image. CNNs follow a hierarchical model that ends with a fully connected layer where all neurons are connected to each other, and the output for something like this, which is a multi-class classification, like picking from one of 1,000 things that could be in an image, they often have their final output chosen by a softmax function. On a personal note, the ZF model shown for 2013 here was created by Matthew Zeeler, who went on to form the AI company Clarifai, where I've worked for the last 2 years. So what is a CNN? Rather than go into the details of what a convolution is, or how it works, let's just focus on how it can work for images. Here is a simple example of a CNN using 2 convolutional layers with max pooling for downsampling. We're using the ever-present MNIST dataset of handwritten numbers used in most introductions to neural networks. An important concept that will become more obviously relevant to our problem is the creation of feature maps. In a CNN, a feature map is the output of a convolutional layer, which is obtained by applying a set of learned filters to the input data. These filters are learned by training the model using backpropagation. During the forward pass of a CNN, the input data is convolved with each filter to produce a set of activation maps, one for each filter. These activation maps are stacked together to form the output of the convolutional layer, the feature map. In the example in this slide, the first layer uses a convolution layer with max pooling to downsample the feature maps. Let's see this in action in the following video. The image is fed into the first convolutional layer that consists of 2 5x5x1 dimensional filters. We'll use a stride of 1. This just means it's moved by 1 pixel as it goes across the image. Sometimes convolutions can have bigger strides to move more pixels at a time, but for simplicity, this just uses 1. We start with the first filter and map the activations onto activation 1 in the first layer. Then, we do the exact same thing for the second filter and map the output onto activation 2. You can see on the left here that we get 2 different results. They're starting to look a lot less like the original image of a handwritten 7. These convolutional results are often referred to as feature maps. Next up is an optional but commonly used method of downsampling called max pooling. Here, we use a pool size of 2x2 and a stride of 2, so it jumps through the image 2 pixels at a time. We run the pooling for each of the feature maps. The idea is that we want to extract only the most activated pixels from the feature maps and shrink the dimensions from 24x24x2 to 12x12x2. So clearly, the idea of making the data smaller as it moves through the CNN is a useful one. If you recall from the first slide of this section, There were two convolutional layers with max pooling. As the data flows through the network, additional feature maps are created at each layer. Since convolutional layers may have multiple stacked filters, we may accumulate more feature maps as we move through the network. In the example above, we have a total of 4 feature maps at the end. These feature maps are then flattened and concatenated together, then fed into a fully connected layer with a softmax, which gives us our prediction. Feature maps can also be useful on their own for separating distinct objects in an image. By applying convolutional filters to an input image, they allow the extraction of important features such as edges. Filters designed specifically for edge detection emphasize abrupt intensity changes in the image, and by using multiple filters at different scales, orientations, and levels of abstraction, convolutional neural networks can effectively detect edges and complex patterns. All this background brings us to the crux of what the GIST paper is trying to solve, which is that models are getting big. It's even become a meme in the machine learning world that deep learning practitioners solve everything by just slapping on more layers. While most of the big news about huge models has been in relation to language models, computer vision models have also experienced significant growth in parameter size over the past few years. These increases in model size have led to improved performance on various tasks, but they also come with their own set of challenges. VIT-G14 shown here has 2 billion parameters. Even models from a few years ago, like its predecessor VIT-Huge14 model, has 632 million parameters. Other examples include large-scale CNNs like ResNet 152 with around 60 million parameters and the largest EfficientNet version with up to 88 million parameters. So why is this important? Here are a couple of reasons. Computational requirements. Larger models demand more memory and processing power, making them expensive and time-consuming to train and sometimes infeasible to deploy on low-resource devices, like mobile phones and edge devices, such as non-internet connected cameras. To solidify the previous idea, Google Brain's paper on VIT-G14 shows that they trained it for more than 10,000 TPU v3 days. It's a bit hard to make out the exact numbers of the logarithmic scale, but assuming that last red dot is halfway to 10 to the 5, that would make it around 30,000 TPU v3 days. Given that a TPU v3 core day represents 1 day of computation using a single TPU v3 chip, which contains 8 TPU cores, that could mean almost 4 days of computation using 1,000 TPUs, or 40 days using 100. No matter how you slice it, that's far more processing power than the average researcher has access to. Energy consumption. Training and running large models consumes significant amounts of energy, which contributes to carbon emissions and raises concerns about the environmental impact of AI research and applications. Accessibility. Due to the high costs associated with training and deploying large models, their benefits may not be equally accessible to researchers, smaller organizations, or individuals with limited resources. Complexity of deep learning models. Modern neural networks have a vast number of parameters and layers, leading to complex interactions and dependencies during training. Developing new training methodologies that can handle this complexity while maintaining performance is a challenging task. Trade-offs. Many solutions that address one aspect of the problem might introduce other challenges or compromise model performance. For example, using model compression techniques like pruning or quantization to reduce memory requirements might lead to a drop in model accuracy or increased training time. Scalability. As neural networks continue to grow in size and complexity, it becomes increasingly difficult to scale training methodologies to accommodate these changes. Some techniques that work well for smaller models may not be effective or efficient for larger models. Heterogeneity. One of the problems of distributed training can be completely different computer systems of varying capability trying to work together in parallel. Similarly, deep learning models and their applications are diverse, spanning computer vision, natural language processing, and reinforcement learning. Developing universal training methodologies that can effectively address the challenges across all domains and model architectures is difficult. Hardware and software dependencies. Training methodologies often rely on specific hardware architectures such as GPUs, TPUs, or custom accelerators, and software frameworks such as TensorFlow or PyTorch. Developing new methodologies that are compatible with existing hardware and software ecosystems can be a complex task. Research and development cycle. Developing new training methodologies often involves a lengthy research and development cycle, including designing, implementing, and testing new ideas, followed by publishing results and integrating them into widely used tools and frameworks. This process can take years, during which the landscape of deep learning models and their challenges may continue to evolve. There are a multitude of ways to approach the memory bottleneck for training complex 100-layer deep networks using GPUs. Some of these efforts include advancements in distributed and parallel training and transfer learning of existing pre-trained models. GIST, however, is trying to solve the GPU memory problem in a very specific way. It introduces a framework for layer-specific optimizations that significantly reduce this memory pressure on GPUs caused by feature maps, also called intermediate layer outputs. Feature maps typically have two uses that are spread far apart temporally. Storing and decoding these feature maps for use in the backward pass during training requires a significant amount of memory. GIST introduces a framework for layer-specific optimizations that significantly reduce this memory pressure on GPUs caused by intermediate layer outputs. We will dive into much more detail on how this works. Now that we've narrowed down the problem from "it's hard to train huge models" to "how can we reduce the memory footprint needed," let's see why other solutions have not been effective. Most methods proposed to reduce the memory footprint in model inference have an emphasis on reducing the model size, specifically the model weights. However, for training, weights are only a small fraction of total memory footprint. Many researchers have recognized this shortcoming and proposed approaches to reduce the memory footprint of deep neural network training. There are three things, however, that the paper points out as goals that prior approaches need to simultaneously achieve. The first is to provide high memory footprint reduction, meaning that the approach should be able to significantly reduce the memory usage of the network training. Low performance overhead. The approach should not significantly slow down the training process of the deep neural network. Reducing memory usage is paramount, but it should not come at the cost of significantly slowing down the training process. This shouldn't be a surprise, but the solution should not come at the cost of significantly reducing the accuracy of the neural network. We need to be able to use a solution which doesn't force us to choose between training cost and the quality of the model. The paper mentions three techniques that have been tried. Prefetch and swap out. This approach involves moving data between CPU and GPU memory. However, it suffers from significant overheads in data transfer, power energy consumption, and performance costs due to swapping data in and out of GPU memory. This means that it fails number 2 on this slide for low performance overhead. Reducing mini-batch size. This technique reduces memory footprint during training, so fulfills the footprint reduction, but it negatively impacts the training runtime as smaller mini-batches lead to GPU underutilization. This means we need more GPUs, which is inefficient since GPUs are expensive and power-hungry. It can also result in poor scaling, which we previously mentioned as one of the things that makes solving this problem difficult. Recompute. This method involves recomputing the output of a layer's forward pass during the backward pass instead of saving it. The issue with this approach is that the largest layers, which uses the most memory, take the longest to recompute. Once again, this is against our goal of low performance overhead. At this point, we're going to start hinting at what the paper solution proposes. Here is a bar graph of memory usage versus specific models, with none of the details of how the memory is being used. Here on the x-axis, there are 5 popular image classification networks as they've evolved over time. As we move to the right in the direction of x increasing, the networks get deeper and more accurate. The y-axis shows the total memory footprint that's allocated for DNN training and reveals the total memory footprint of DNN training is very high. Especially for the last 2 networks, VGG16 and Inception, if we want to go for a larger batch size, that is, if we want to process more input images in parallel, the memory footprint exceeds the DRAM size. This problem gets worse for the deeper DNNs that have an even higher memory footprint. This shows a trend. Modern DNNs often have memory footprints that exceed their DRAM size. This takes us to our main focus. GPU DRAM capacity becomes the primary blocker preventing us from making DNNs that are deeper and as a result more accurate. So here's the burning question. Why is this memory footprint so high? To answer that, here's another look at the same graph, but with a breakdown of footprints across different training data structures. These contain weights, gradients, and feature maps, as well as workspace overhead. We can safely ignore the majority of the colors. What we care about are the huge red parts, because those represent the memory used by the feature maps, the primary contributors to the total memory footprint. As we move right, it's clear that as the networks get deeper, this amount of red becomes more and more prominent. In contrast to inference, where weights are the primary contributors, this raises the question, where is this memory footprint coming from? What are these feature maps? To understand this better, let's take a look at a very simple DNN training example. Here, we have a very simplistic view of a DNN and its layers in training. When training, we use 2 passes. The first one is the forward pass, where we take the inputs, propagate them in the forward direction, and get a prediction. In the backward pass, we take this prediction, find out what the error is, propagate that error in the backward direction, and update the weights to improve the accuracy. So now, zooming into layer 2, let's take a look at one of these layers and all its associated data structures. In the forward pass, this layer gets a feature map x and calculates a feature map y. In the backward pass, it takes a gradient map dy and calculates a gradient map dx. If you look at the backward pass calculation, it's computing dx, which is a function of x, y, and dy. And these x and y values are the feature maps from the previous slide that we need to save for the backward pass calculation. Therefore, as a network gets deeper, there are more and more feature maps to be saved, which requires a larger memory footprint. It's clear that reducing the memory footprint of these feature maps will enable the training of deeper DNNs. Let's walk through an example of how this idea could happen. Here we have a single layer, a ReLU layer, which is very common in convolutional neural networks. The ReLU function takes in an input x, and if the value x is positive, the ReLU function returns the input value itself. If the input value is negative or 0, the function returns 0. The purpose of the ReLU function is to introduce non-linearity into the network. We have its output, which is a feature map. Now let's see where this feature map is used. The first use is immediately in the forward direction, which is a pooling layer, and then the forward pass and backward pass begin. The second use is much later, in the backward direction, when we perform the backward pass calculation of the ReLU layer. What we observe is that there is a very large temporal gap between the first and the second use, and in this gap, the data is sitting in the GPU DRAM. During this large temporal gap, we store the data in a much smaller format. Throughout this computational timeline, the data for the baseline is stored in a format called FP32, which stands for a 32-bit floating point. In the paper's approach, we store the data in FP32 format only until the first use. But during that large temporal gap, the data is stored in a much smaller format. Just before the backward pass is about to happen, we decode the data back into FP32 format, and we make 3 key observations that let us design very aggressive data encodings for this large temporal gap. These data encodings are designed solely to reduce the memory footprints of feature maps. 2 of these data encodings are lossless. That is, they do not affect the application's accuracy. One of them is called binarize, which focuses on the feature map between the ReLU and the pool layer, and the second one is called sparse storage dense compute, which focuses on the feature map between ReLU and the convolution layer. The last encoding is a lossy encoding, which means it can affect the accuracy of the DNN training. They call this encoding delayed precision reduction, and it is applicable in a more generic manner. Let's examine where we can use each of these encodings. Let's start with the binarize encoding. Once again, here is the same DNN layer and all its associated data structures, and the backward pass calculation is dx, which is a function of x, y, and dy. Current deep learning frameworks, at least as of 2018 when this paper was written, view neural networks in a layer-agnostic manner. That is, despite the wide variety of layer types and functions, the frameworks treat them all the same. By examining this calculation, the paper's authors found very high data redundancy. Specifically, by taking a closer look at the backward pass calculation of the ReLU layer, they found that the dx is not a function of x. It only depends on y and dy. In addition, it only needs to know whether the value for y was positive or negative. So during that large temporal gap, the only data that needs to be stored is whether the value of y is greater than 0. That information can be stored in just 1 bit instead of 32 bits. Similarly, for the pooling layer, we see that we do not need to store both x and y. What we need to store is a mapping of locations from x to y, and this mapping can be stored in a very small format compared to both x and y. Therefore, our first insight was that if we take the layer types into account, it reveals the presence of very high redundancy. Based on that, the paper presents binarize encoding, where they take the feature map between the ReLU and pool and store it in just 1 bit for the large temporal gap. Since we're going from 32 bits to 1, this represents a compression factor of 32x. Here's an example of binarize, and as you can see, it's very simple. ReLU only lets values through that are non-negative, and then binarize sets those to 1. Unfortunately, the authors found that the binarize encoding is not applicable to the ReLU convolution feature map, which also takes up substantial space in the feature map memory footprint. Fortunately, they found that there is a large amount of sparsity in DNN training. A neural network is considered sparse when many of its weights, activations, or gradients have values equal to 0 or close to 0. This means a significant portion of its elements have negligible or no contribution to the network's computation. Based on the author's observations of sparsity, they created the sparse storage dense compute encoding using CSR, which is shown here. CSR encoding consists of 3 separate one-dimensional arrays: row pointers, column offsets, and data. This array stores all the non-zero elements of the sparse matrix in a row-wise order, that is from left to right and top to bottom. Row pointers. This array stores the index in the values array where a new row starts. The first element is always 0, indicating the start, and the last element is equal to the total number of non-zero elements in the matrix. Column offsets. This array stores the respective column indices of each non-zero element found in the values array. Data. This array stores all the non-zero elements of the sparse matrix in a row-wise order, i.e. from left to right and top to bottom. It is the same length as the column offsets array. As the name suggests, we store the data in a sparse format during the large temporal gap, but the calculations are performed in a dense format because sparse computations map very poorly on the GPU architecture. In addition, the authors wanted to keep the advantages of the highly optimized NVIDIA encoding library in the test format. So far, we've only covered lossless encodings. Now let's look at the lossy encoding. So here we're showing you 4 layers in the forward pass. Directly below the forward pass, we have the same 4 layers in the backward pass. As stated earlier, each feature map has 2 uses, one immediately in the forward pass and one much later in the backward pass. The second use is shown here with the help of these vertical arrows. In CNN inference, we can apply something called precision reduction. We can reduce the number of bits needed to represent the data, and we still get very good accuracy in inference. But if we use the same precision reduction method in training, it makes the accuracy very poor. In this experiment, the computation is performed in FP32 format. The computation is unmodified as it's being performed on GPUs. Now, if we apply the precision reduction in the same manner we apply to inference, we'll apply it to all these edges. The connections where precision reduction has been applied is represented in the diagram by the blue lines. Now, when we calculate layer 1 and we apply this precision reduction at the end, we get some error. This error goes into layer 2 and possibly gets magnified, and as we move in the forward direction, this error becomes greater and greater until finally it causes catastrophic harm to the training of the model. AlexNet, even in FP16 format, stops training at this point. This lossy encoding was fine for inference because at inference the training has already been completed and the weights have already been set. However, the goal of training is to update the weight so that we can get better accuracy. So, using sparse storage dense compute encoding in the forward pass during training quickly lowers accuracy. To fix this problem, we do not apply precision reduction everywhere. We will change the design so that the blue precision reduction arrows are only connecting the second use of the feature map. We only apply it to that large temporal gap, so our encoding is kept in FP32 format until after the first use. During the large temporal gap, however, the data is stored in a much smaller format, and we can see that if we apply the precision reduction at this point, we can save a lot of memory without affecting the accuracy of the application. The paper calls this encoding delayed precision reduction and presents 3 different configurations, FP16, FP10, and FP8. These correspond to 16, 10, and 8-bit floating point numbers. This concludes the descriptions of the 3 encodings. Putting it all together, the paper presents a system called GIST, which is a runtime system that enables the training of DNNs by reducing the memory footprint of DNN feature maps. Here, we show a DNN and its execution graph. The execution graph is an abstraction of the compiler that is often used in deep learning frameworks today. GIST inspects this execution graph and identifies all the encoding opportunities. Can we apply lossless encoding? Can we apply lossy encoding? And based on that, it builds a static schedule for how all of these different data structures will be used. Then, it adds the functions to encode and decode to the right places in this execution graph. This new execution graph is then used for the DNN training. The second responsibility of GIST is to perform efficient memory sharing. Because we are allocating these new encoded and decoded data structures, we need to allocate the memory in an efficient way to reduce the memory footprint. The framework uses the CNTK, Microsoft Cognitive Toolkit, memory allocator to find an efficient static memory sharing strategy based on the lifetimes of various data structures. The schedule builder component of GIST performs liveness analysis to determine the lifetime of affected feature maps and presents this information to the CNTK memory allocator for optimization. The authors evaluate GIST memory reduction capabilities on the Microsoft CNTK deep learning framework, and they implement their encode and decode functions in CUDA to perform this evaluation. The evaluation is performed on an NVIDIA Maxwell GTX Titan X with 12 GB of GPU DRAM. GIST is then evaluated across 6 state-of-the-art image classification CNNs: AlexNet, Network in Network, Overfeet, VGG16, Inception, and ResNet. By comparing the results across 6 different CNNs and gathering a significant number of metrics, the paper sufficiently proves its claims. To measure the effectiveness of GIST through said experimentation, the authors looked at the effective compression ratio. To measure this effective compression ratio, the authors utilize a baseline in the CNTK original static memory allocation strategy that does not utilize any optimizations. In the baseline, the data is stashed in a single precision FP32. Then recall that there are 2 lossless encodings, which are binarized in SSDC, and 1 lossy encoding, which is delayed precision reduction. For the lossy encoding, the smallest representation is used, which has the same accuracy as the FP32 baseline. The results here show that there's no accuracy loss between FP32 and GIST. Here on the x-axis are the different CNNs, and on the y-axis, the effective compression ratio achieved against a CNTK baseline. The second bar shows you how much data can be compressed using only lossless encodings compared to a baseline. The third bar shows the additional savings that you get by applying lossy encodings on top of lossless. Overall, GIST achieves a 1.4x compression when only lossless encodings are applied, and 1.8x when both lossless and lossy encodings are applied. However, compression is only one half of the story when examining the effectiveness of GIST. The other side is the performance overhead. And since all these encodings were designed with GPU architecture in mind, All of them are highly parallel, and it is found that all these savings can be achieved with only 4% performance overhead on average. Only the Inception model is slightly higher, with a maximum of 6% performance overhead. GIST also has an impact on machine learning trends, specifically on how neural networks are getting deeper and deeper. And as the networks get deeper, the largest batch size that can fit in the GPU memory becomes smaller and smaller, and you run the risk of underutilizing your GPU hardware. By reducing the amount of memory used, GIST lets you run larger batch sizes and use your GPU hardware more efficiently. In this experiment, the authors studied the impact of GIST on performance improvement. Here, they use ResNet for this study because it allows them to vary the depth of the network very easily. On the x-axis, there are 3 different lengths of ResNet: 509 layers, 851 layers, and 1202 layers. On the y-axis is the speed improvement achieved by GIST against a baseline. And these are the results. The number on the bar shows the largest batch size that can fit on the GPU. For example, for the first bar in ResNet 851, the baseline only fits a batch size of 16, but with GIST, that can be increased to a larger base of 32. Moving to the right on the graph, as the networks become deeper, the benefit of using larger batch sizes becomes higher and higher. In the bar for ResNet 1202, GIST achieves a 23% performance improvement for a very deep ResNet network. The authors conclude that modern DNN training has a very high memory footprint that often exceeds DRAM size, and it observes that feature maps are the primary contributors to this large memory footprint. In addition, there is a large temporal gap between 2 uses of a feature map, which results in a very high amount of data redundancy. It's based on this that the 3 data encodings were designed, and through which GIST can achieve up to 2 times compression with only 4% overhead. For further investigation, the paper's primary focus was on the ReLU pool and ReLU convolutional layers, but other lossless encoding options exist that can be tested with GIST. Furthermore, the research focused almost entirely on convolutional neural networks. Today, the largest models are transformer-based large language models. Can GIST be applied to a different model such as this and yield the same performance-enhancing results? Just for fun, we asked ChatGPT what it thought about all this. It agrees. It mentioned that GIST could potentially be beneficial for GPT-3 in some ways, such as reducing memory usage during training and inference. It shared our thought that this warrants further investigation. As a side note, ChatGPT then hallucinated that GIST stands for Generative Interpretable Semantic Trees, which is not mentioned anywhere in the paper. This part was difficult to come up with due to the incredibly specific subject matter and rigorous testing that the researchers performed. However, we were able to come up with 4 potential assumptions that might deserve a closer look. First up, applicability of encodings. The encodings proposed in this paper may be tailored to specific types of layers, but they assume that these layers are present in the network. For instance, if a network does not utilize ReLU or pool layers, then the lossless encodings, whether binarized or SSDC, wouldn't be of any use. The paper makes it sound like GIST is a tool that can fix a broader spectrum of DNNs than it really can. Secondly, in-place computation assumption. The paper assumes that in-place computation is helpful in reducing the immediately consumed data structures in memory. However, in-place computation might not always be possible or efficient, depending on the specific architecture or implementation of the DNN. Thirdly, performance overhead. While GIST reduces memory footprint with only a 4% performance overhead, it does not fully explore the trade-offs between compression and performance. Depending on the specific network architecture and implementation, the performance overhead may vary and could potentially be more significant. And finally, non-portability of GIST encodings. While the paper demonstrates the implementation of GIST encodings within the CNTK deep learning framework, the applicability of these encodings in other frameworks is not evaluated. The effectiveness, portability, and ease of implementing GIST encodings in different frameworks remain unexplored. To sum up, we saw that modern DNN training has a very high memory footprint, which often exceeds DRAM size. We also saw that feature maps are the primary contributors to this large memory footprint. We observed that there is a large temporal gap between the 2 uses of a feature map, and that there's a very high amount of data redundancy for these feature maps. Based on this, 3 data encodings were designed: binarized, sparse storage dense compute, and delayed precision reduction. And finally, using these 3 data encodings, GIST achieves up to a 2x compression with only 4% performance overhead. This concludes this presentation on GIST. I hope it was informative and useful, and thanks for watching.